Hello everyone, I'm Xunjiang from Cardiff University. Here I'm very glad to share with you the research in my thesis. And the title of my thesis is Feasible Operation Region of an Electricity Distribution Network with SOPs. Looking at the title, you may have some questions about the feasible operation region and SOPs. And through this presentation, I hope you can get answers and learn something new. Okay, so firstly, let me briefly introduce you to the background. And my thesis focuses on electricity distribution networks. And for net zero target, there will be increasing low carbon technologies integrated to distribution networks. And these technologies include low carbon renewable generation, energy storage, and also electrification technologies in different sectors. And according to the predictions by the World Energy Outlook, the total electricity generation and demand will double by 2050 compared to the current status. In particularly, the distributed PV systems and electrified transport like electric vehicles will see a dramatic increase in distribution network. So the question is, are our distribution networks ready for these collections? And answer is not yet. So we need to upgrade the distribution networks to increase their hosting capacity. However, the conventional network reinforcement normally means high cost, negative social and environmental impact, and also non-permitting construction time. So to avoid these problems, an alternative solution termed as soft-open point has been widely implemented across the world. And the idea of SOP is very simple, just to replace the existing normally open points of distribution network with some advanced power electronic devices. And with flexible power control, our SOPs network capacity can be fully utilized so that we can defer conventional reinforcement. So we've been talking about hosting capacity. So how do we assess hosting capacity? So the existing assessment method normally calculate hosting capacity of the network based on scenarios, such as worst-case scenario commonly used by power companies. And these worst-case scenarios include maximum generation, minimum demand, and maximum demand, minimum generation as well. And these worst-case scenario-based assessments are very conservative, which leads to network capacity not efficiently used. And another problem is that worst-case scenarios will be very hard to be identified in the future with increasing uncertainties from renewable generation and electrified demand like electric vehicles. So this makes me rethink the hosting capacity methodology and take this cup for example. A question is the capacity of the cup affected by how much water it hosts? The answer is obviously no. And the capacity of a cup is only determined by the shape and parameters of the cup itself. So turn to distribution network. We can ask the same question. Is the hosting capacity of the network will be affected by the scenarios for the power generation or node it hosts? I think the answer is the same. So the aim of my thesis is to try to develop a tool for describing the overall picture of the network capacity, which is only associated with the network itself and remains unaffected by the scenarios for the power generation or load. Okay, so to achieve this goal, I define feasible operation region as the allowable range of the operating states of a distribution network where the network constraints are not violated. And I will use this very simple case here to work with you to construct the feasible operation region for P2 and P3. Okay, so here's a map for P2 and P3, and we randomly generate a operating state here, and we run power flow simulation to see whether the constraints are violated. If not, we will deem this operating state as a feasible one. And we can do it repeatedly to generate as much as possible feasible operating states on the map. And if the operating state violates at least one of the network constraints, we will deem it as an infeasible one. Okay, imagine we can obtain all the feasible and infeasible operating states on the P2, P3 map, and then we can enclose all the feasible ones within a region, and this region is actually feasible operation region. And this example tells us how to construct a two-dimensional feasible operation region. But for a distribution network, it normally has multiple nodes and multiple power injections. So in this case, how can we describe the feasible operation region? So in the first work of my thesis, I tried to express FR boundaries to describe the FR. And the right-hand side figure shows you 4 two-dimensional cross-sections of the FR for benchmark UK distribution network. And let's first focus on the regions with different colors. The green regions in the figures represent the FR, while the regions with other colors represent infeasible operation regions that violate different network constraints that include the line current constraints and also voltage constraints. So the first finding is that corresponding to each of these network constraints, the FR boundaries can be classified into thermal boundaries and voltage boundaries. Okay, so let's move on to focus on the blue lines and red lines on the figures. Actually, we can use different analytic expressions for FR boundaries. And here I compare the quadratic expressions, which are the red lines, with the hyperplane expressions, which are the blue lines here. And the conclusion is that both expressions can well approximate voltage boundaries. However, for thermal boundaries, quadratic expressions present more accuracy. Okay, so now that we have a better understanding of the FR, and the next question is if we have SOPs, how SOPs can impact the FR. And the conclusion is that SOPs can really extend the FR boundaries in a way that the FR of the network with SOPs can be actually modeled as the Minkowski sum of the FR of the network itself and operating range of SOPs. And here I will use this three-dimensional FR for an example, and to clearly demonstrate the results, I further use these 5 two-dimensional slices for your observation. And we can see that if we put the operating range of SOPs on the red boundaries and sweep the boundaries, and finally we can see that the outermost points after this sweeping operation is exactly the new boundaries with SOP. So this sweeping operation is actually the geometric representation of Minkowski sum, and this is the second contribution in my thesis. And the third question in my thesis is how to use FR to control the SOP. So I further developed a novel FR-based optimal power flow model. And compared to the conventional OPF model, the FR-based model can firstly adapt to various measurement conditions. And we can see from right-hand side figure, even equipped with limited measurement units, it can achieve near global results. And from the results in this table, you can see that it can also rapidly generate SOP set point within a few hundred milliseconds, which means it can be applied in real-time operational network. And all the outcomes have been published in these papers, with one paper still under review. If you are interested in this topic, you could check out these papers, and you are very welcome to email me if any questions. And thank you very much for listening.